All right, so let us begin. So you know about quadratic equations. Okay, you know about quadratic equations in the sense that they are of the form ax square plus bx plus c equals to 0. And you can easily solve it. You can have this uh, quadratic equation roots as, let's say, minus b plus minus this formula. It's pretty well known to everyone. Okay. Now, I gave you one equation to solve that if this equation involves something like transcendental functions, like say x cos x minus e to the power x equals to 0, how you can find x here? How you can find x which satisfies this? Of course, you cannot rely on, cannot rely on analytical methods. Yes, you cannot rely on analytical methods. So there you have to rely on numerical methods. Okay. Why you cannot rely on analytical method? The analytical method which can solve this? Anyone? No? Okay. So what you can do is you can solve it graphically. Solve it graphically. How you can solve it graphically? Let us do this quickly. For this, I use a very nice tool which is known as Desmos. I think many of you might have learned about it already. Say y equals to x cos x. Okay. Fine. It gave me the plot. Then another y equals to e to the power x. Okay. So you can see here, you can see just from here that these are the two curves. The red one is y equals to x cos x, and the blue one is y equals to e to the power x. And where it intersects is the root. Okay. Because where it intersects is the root. Why it's the root? Because there the value of y for both x cos x and e to the power x are the same. So if I do another way, say x cos x minus e to the power x equals to 0. Okay. So therefore, yes. So this is giving you the range, the list of solutions x, which is satisfying this equation. Okay. So this is just one of the examples I showed you. Just one of the example I showed you where you can solve it graphically, any kind of equation. Okay. What you can do is treat it like fx equals to g of x and find common point of intersection. Yes. Fine with you? Now, but how you can actually use computer to find it? You will not always use the graphical method. Okay. Graphical method might not be at your disposal every time. How you will do it? Therefore, this is where numerical methods comes. This is where come. Okay. There are a lot of different numerical methods to solve these kind of transcendental equations. Okay. Any complicated equations you give, we are not bothered by it. We just have to evaluate the function. Now, there are two things I would like to ask. First, can you find the root of this equation? Can you find the root of this? Can you find root of x cos x minus e to the power x equals to 0? Second question is, can you evaluate the function x cos x minus e to the power x at any given x, at any given value of x? Which one is easier, first or second? Say step 2, I can say fx equals to x cos x minus e to the power x, and I say find f of 2. Is this easy? Second step is easy. Okay. So scientists also thought about it. Okay. Scientists thought that yes, if finding the function value is easy, can we use this idea to find the root? Can we use the idea of second step to find the root of the function fx equals to 0? Okay. Now x equals to what? Such that f of x equals to 0. That is our aim, isn't it? That's what we are exploring here. Fine. Everyone understood this part or no? Okay. To do that, we will just evaluate the function in such a way that fx turns out to be 0 or close to 0. Then we will say we have the root. Okay. So now we will devise a method now, which is known as a bisection method. Okay. Which will help us to find the root of this kind of equations just depending on the function evaluation. Okay, nothing more. Let us look into that. Okay. So you might have seen f of x when f of x is some linear function, say ax equal to b, linear, and because ax equal to b equals to 0, that will just give x to be minus b upon a. Fine. But if the equations are not of this form, then they are nonlinear functions. Okay. Nonlinear or nonlinear equations, I would say. Okay. And solving such kind of nonlinear equations, solving such nonlinear equations need numerical methods. Okay. That's where computational science come. All right. So now we'll see that. So suppose you saw that, right? Like maybe what I can draw, maybe I can draw a sketch here. Say this is x and this is y. Okay. You can always represent the function, right, on the xy plane. Yes. So I'll just represent it. Okay. Fine. So say this is y equals to fx or fx equals to 0. Okay. Fine. Fine with you. Okay. Now, where is the root? Can you tell me? Where is the root? Where is the root here? First column. So the root will be wherever it intersects. Straightforward, right? So this is the root. Okay. This is the root because this is the value of x which makes fx to be 0. Okay. It's wrong here to write this. Y equals to fx. Okay. And this is the point root where f of x is equals to 0. Fine. Now our job is to find this value of x so that we can tell that yes, we have found the root of this equation. Okay. For that, we do a clever trick. We do a clever trick of function evaluation. What we do, say I will select this pink. So we will take 2 points, such 2 points such that the sign of the function are different. Okay. So say this is a, this is b. Okay. Now what is f of a? F of a is less than 0. Fine. Why f of a is less than 0? Because it is on the negative y-axis. It is on the negative y-axis. Fine. How many of you could not get it? See, this is the y here, right? This is the y part. So it is on the negative y-axis. So this is negative. So therefore f of a is less than 0. Similarly, this is b and this is lying on the positive y-axis. So you can say f of b is greater than 0. Yes. Now I'll ask you, what is the product of fa times fb? It should be less than 0 because one is positive, one is negative. Okay. So this should be less than 0. Yes. So our first step of this method is to find an interval. Okay. Step 1 is find an interval. Okay. Find an interval. Say AB or x1, x2, maybe I will tell, such that f of x1 times f of x2 is less than 0. Okay, fine with you. Why we need to have this? Why we need to have this condition? Note that if you have this condition, that is one is negative, one is positive, then by intermediate value theorem, I think many of you might have known in your class 12th, if you have a function if it is a continuous function, okay, and in that continuous function you have a value less than 0, at another value you have the function value greater than 0, then there exists a point in between those two where f should be equal to 0. Yes, because logically, if you think, if you are not from a math background, logically, if you think, if it is a continuous function, that means you can draw it by your hand without lifting up your pen. Okay. Then what you do, if it is negative at one point, if it is positive at one point, then you are sure that suddenly it can't transit from negative to positive because it's a continuous function. It can only transit through 0 to become positive. Okay. Understood this? So therefore, this is the logic behind it. Okay. So therefore, we take an interval a and b, or say x1 and x2 here, such that f of x1 and f of x2 are of different sign only because the root is in between the two, x1 and x2. Can you see that the root is in between these two? Okay. Now our idea is one thing, that is we will decrease the size of this interval. Now tell me, if you keep on decreasing the size of this interval, you're slowly approaching this root. That is the basic idea of this method. We will evaluate the method iteratively again and again by decreasing this interval. Okay. How? That's our aim. Second is iteratively reduce this distance mod x1 minus x2. You can see mod x1 minus x2 is this guy here. Okay, we will try to reduce this interval. Now you can see that we will approach the root. Okay. Yeah. Let us take the first iteration so that you understand it. You have, so what you did now is you found x1 and x2, okay, such that the multiplication of both the function is are of sign, like that is less than 0. Got by you? Clear with everyone? Okay. Now next step is what you do next. Okay, you did that. You found x1 and x2, but what is the step 2? Step 2 is the first iteration. The next iteration is you take the middle point of those two, x1 plus x2 by 2. Okay, where should it lie? Where should it lie here? Suppose this point in blue. Okay, suppose this is the blue point, which is the midpoint of x1 and x2. Okay, fine. So this should be your x1, x superscript 1. That is the first iteration. If it is the second iteration, we will use x superscript 2. Just to, this is the notation we will follow. Okay, so this is x1 plus x2 by 2. Then what you do? I told you that we will just evaluate the function, nothing else. Depending on the evaluation of the function only, we will find the root. Okay. Now, what we do is, if f of x1, you can always evaluate f of x1, isn't it? At this new step, at the middle point. Then multiply it with x2. Okay. If this is less than 0, then your root should be in between those 2 points. If this is true, what does this mean? Root lies in between x of 1 and x2. Okay, fine. There can be another possibility. What other possibility it has? This f of x1 times f of x1 is less than 0. This is another possibility. It can be with the first point or it can be with the last point. Either multiplication of this function and this less than 0, or multiplication of this function and this is less than 0. Two possibilities. If this is less than 0, then that implies the root lies in between, say, x of 1 and x1. Now, which case we have here? Let us see. Let us you compute at x1 what is the value of f. It's positive, right? Because it is lying here. Yes. Now, is f of x1 into f of x2 less than 0? First step true. Is this one true? What do you think? Why? Because f of x1 is positive, f of x2, this quantity is positive, sorry, this quantity is positive, isn't it? Everyone agree? How it is positive? You can just draw a vertical line and see it is in the positive y-axis. Okay, this is positive. Is f of x2 positive? F of x2 is positive, so it can't be less than 0. So this case is not valid here for our example. What other case is there? F of x1 into f of x subscript 1. So f of superscript 1, it is positive, fine. Now this was x1. This is less than 0. The function is less than 0. The value of the function is less than 0, fine. So this is less than 0, so the product is negative. So what does it mean? It means the root lies in between x1 and x superscript 1 and x1. Now what should be our next step? What should be our region of search? The region of search should be in between, isn't it? Instead of this big guy, instead of this big black interval, the region of search should be narrowed down to x1 to the new point found. Through that, you can understand that how the interval got reduced. Can you understand that the interval is getting reduced? Can you see that the black interval is bigger, or sorry, the red interval is much smaller than the black interval? Can you get that? Okay. Now, so if this is true, search the root in between x of 1 and x1. That's fine. Okay. Now x1 you have already termed it as x1. Okay. But what is x2? X2 was this one. We always search root in between x1 and x2. So that means you have to update x2 now. x1 is already fixed. x1 is already x1, but x2 can be changed to this guy. Then the method will be more effective. So through this, you update x2. This is the arrow we give to update the x2. The value of x2, instead of b, it will now be updated to x of 1. That is this value. Previously, it was this value. Now x2 is this guy. Can you see that? Can you understand? If x2 is this guy, now can you see that this is the point x1 and this is the point x2? And you have to now search in between these two instead of the black interval. Okay, fine. Now second iteration, what you do? Second iteration, you take the middle point of x1 and x2 again. These 2 points. So this will be this point, right? This will be x1 plus x2 by 2. Fine. What this point should be, this is the second iteration. So x2 equals to, yes. Are you getting it? Yeah. Now what you should check the value, second iteration, check the value of f of x2, okay, and f of x1 if it is less than 0. Another possibility is f of x2 and f of, yeah, I'll stop something randomly. You should tell me that. X2, yes, f of x2 is less than 0. These are the two possibilities we have. Either the multiplication of this point with this point is less than 0, or multiplication of this point and this point is less than 0. Both cases cannot happen. Due to your starting condition, both of the cases cannot happen simultaneously. Okay. Got it? So now, depending on that, either you need to update x1 or you need to update x2. Either way, the interval will reduce than the red interval. Okay. So you can see now the interval is reducing. I would say that the x1 will be updated. Okay, this one will be the new x1. So now the region of search is this. Can you see that this is the first iteration? This is the first iteration. The red one is the second iteration. The blue one is the third iteration. Can you see how the interval of the route is reducing? Okay. So if it is reducing at one point, you will collide with the route. Okay. So how far you will go? That's the question. Okay, that's the question. Maybe the bridge. How far to go? Can you answer? How far to go? You see, every iteration, your distance is decreasing and you're approaching the route. But can you go on like this for infinite times? Because computer has a memory. It cannot go infinite amount of time. So you have to stop. Okay, you have to stop. So therefore, you will stop if x1 minus x2, say I will say kth iteration, I will tell you in the programming during that point. So if this is less than epsilon, okay, what is epsilon? This is less than, up to you. If you want the distance to be 0.01 apart, so you stop the algorithm, fine. If you say, no, I want more accurate, 0.001 distance, fine, you can go up to that. Less than 10 to the power minus 6, fine, you can go up to that. Depending on how accurate you want the route. But all these steps, the iterations increases. That means the computation time increases. Fine. Got the idea, basic idea behind this? Now, you should question yourself. Okay, sir told me this method, but why should I believe sir? Why should you believe me? Okay, I told this method is there, but why you should believe? I have not yet shown that this is the method. It converges to a root. I never showed it. Okay, so this we will discuss. Okay, this we will discuss in the upcoming class. Fine. I will show to you that indeed under like lot of iterations, you are actually approaching the root, okay? The desired root. Fine. Then I will discuss now. Now the case arises: is bisection method is everything in our literature right now? Can bisection method fail? Can bisection method fail? What do you think? Can it fail? Hmm? When? Hmm? Yes, yes. If you don't have a continuous function, definitely it will fail. Any other? That's known. But in assumption, we start with a continuous function. But I'm saying, even if you have a continuous function which you can draw, see, this is a continuous function. I can draw a function now and show it to you that bisection method fails. Can you give me an example? Huh? Huh. Yeah, that is another case that doesn't have a root. That means you are saying the function doesn't have a root at all. Yes. Multiple roots. Are you saying multiple roots? Yeah, multiple roots means yeah. If you are saying y, I think you are saying y equal to x square. That means it is like bad drawing. Uh, that this is y equal to x square. Okay. So no, this is not the y equal to x square. Maybe good idea would be to first draw this. Okay, then draw the axis. Okay, so this is y equals to x square graph. Fine. This is y equals to x square. What we are saying? Okay, I understood your argument. He was saying one more thing. Maybe. Okay. Let us rub this one off. Just so just ignore this thing. But yeah, treat this as x-axis and y-axis. Fine. So these two are the roots. Are you seeing that? Yeah. So now can bisection method work here? There are two roots now. Yes, it can work. Why it cannot work? Of course, you need two iterations. Why? Maybe you can take this interval and this interval as x1 and x2 and find this root. And later, what you can do, take this interval and find this root. But you need two steps to do. But I'm saying there is also another function where it fails. Can you draw a function based on that? If the interval and the roots are too close, yes, you are 90% correct. But 10% will be correct if you draw a graph. Previous graph is enough. How? Huh. Translate it to or what? Mm-hmm. Yeah. So yes, that's what is the tolerance is needed. The distance will gradually decrease, keep on decreasing. I think exponentially. The distance, how the distance decreases. I will show to you that the distance decreases exponentially. Sorry, not exponentially. In a polynomial order. Okay, not exponential, but in a polynomial order of the range like 2 to the power k. Okay, in that polynomial order it will decrease. But I'm asking that is there a function which can help you think that this can't be applied? You are almost correct actually, but the way you are saying is not. Oh, anyway, I'll just show you. Yes. So this I had already saved from Desmos. So this is one example of a function. Okay. Don't worry about this complicated function, but this is just an example of a function just to illustrate that this is the root of that function. Okay. But finding that interval is very tricky here. Finding that, okay. In these cases, the bisection method will fail. Okay. I urge you to think why it fails. Why it fails? If you think the slope is infinity, there is no slope. Okay, if the slope at the root, the slope at the root, what is the slope at the root? It's vertical. The tangent is vertical, isn't it? No, the tangent is not zero. Yes, tan 90. What is tan 90? Okay, it is not parallel to x-axis. Otherwise, it should be zero. It is 90. It is tangent is parallel to y-axis. So if you have a slope perpendicular, which you are saying that the interval in which the root is lying is very small. Another way of saying it. So in these kind of cases, bisection method fails. Okay, I leave to you to explore this, why it fails and all this. But make sure that any function which has a perpendicular on the x-axis, where the tangent is perpendicular, or tangent is like the slope is infinity, there the bisection method fails. Okay. Anyway, so I think I took a lot of time, is it? No, 5 minutes extra. Okay. So maybe we'll meet at 1:30. Okay. We'll meet at 1:30 and then we'll solve a problem by hand. Okay. If you have brought your calculator in the first class, make sure you use the calculator. If not, make available the calculator app on your mobile. Okay. Feed the numbers and try to solve it. Okay. Calculator. We'll first 20 minutes we will solve by hand. The next time we will do a Python code based on it. Okay. Those who have the laptop should make Google Colab available. All of you have Google signed in versions. How many you have laptops? How many of you have Google Colab with them? No. Okay. So what you have to do is just go to Google Colab. Okay. Just go to Google Colab. Maybe one way to show is this. Go to Google Colab, okay? Yes, and then sign in. Then just use your mail ID and sign in here. Then you will have your own, you can create your own notebooks and you can write your own Python programs there without installing Python also. So I urge you, you do this step before coming at 1:30. Okay, everyone got this idea? Just search Google Colab and sign in using your mail ID. Sign. No Wi-Fi. Take my Wi-Fi. Okay, I'll give you my Wi-Fi. Anyway, don't bother about it. I'll give you my Wi-Fi. So 20 students using my good. Okay, so we'll do that, no worries. So, but I'll make sure that you at least learn something, programming aspect of this course by today also. So we'll meet at 1:30. This room, right? 216, 217.